We're on to question 6 in this Fp2 June 15 paper now. Polar coordinates, not always the most popular type of questions, but they've been quite nice to us here. Pretty standard. There's nothing really hard to work in part B, working out the limits, working out areas, a bit of integration, but at this level I think we should be kind of, if we're worried about polar coordinates at all, a little bit relieved at this. It's saying that there's a tangent parallel to the initial line here. So we know that for this case dy by d theta has to be equal to 0 there. So we've got dy by d theta. So y is equal to r sine theta. Do check. Often, we've got theta here, y sine theta here, so it shouldn't be something you need to learn by rote. So we've got y is equal to r sine theta. So y is equal to 3a 1 plus cos theta times sine theta. So we just need to differentiate that. So dy by d theta, let's use the product rule. The 3a is irrelevant really, but I'll keep it there obviously. Differentiate the 1 plus cos theta, that's minus sine theta, times by sine theta. And then differentiate the sine theta, that's cos theta, times 1 plus cos theta, product rule, without making a fuss of it. Right, obviously this dy by d theta equals to 0. So obviously the 3a is going to go, and we're going to have minus sine squared theta plus cos theta plus cos squared theta equals to 0. Right, okay, so in this case it would probably be as well to change the sine squared to 1 minus cos squared. Plus cos theta plus cos squared theta equals 0. So we have 2 cos squared theta plus cos theta minus 1 equals to 0. Okay, let's see if that factorizes. That's 2 cos theta and we're going to have a minus 1 here and a plus 1 here. Right, okay, now 2 cos theta equals to 1 and cos theta equals to minus 1. Cos theta equals to a half. Right, okay, so we're only interested in this particular solution here. We'll mention what this is all about here. You might wonder, well, what's that about? It's actually to do with the fact this is a cardioid set, and actually on the other side of this bit here, it's almost kind of coming in at tangent that way on our cardioid, which is why we've got the minus pi, the minus 1. So that's not the one we want here, because that's almost like the kind of bogus one, if you like, that's coming in at that point. So it's cos theta equals to a half. So that's theta equals to pi by 3. So that gives us, and we can put half back into here, and that gives us r equals to 9a over 2. So let's just write the polar coordinate just to make it clear. A, 9a over 2 pi by 3. So that was a nice 6 marks really, wasn't it? Not too difficult at all. and neither is part B. It's probably worth thinking here that we shouldn't be in the mindset that one particular topic is always going to be hard. Polar coordinates can be problematic, there's no doubt about that, but this is not a question that is particularly difficult. So it's not good to be in a mindset where you can't do a particular topic. This one is pretty standard, so it should be no problem to us at all. Right, now here we've got A as we've got this is the line, if you like. We've already found the polar coordinate for this, but this is the line theta is equal to pi by 3 and naught. So this is sweeping around. Those are our limits, are just naught and pi by 3. So the required area is equal to half pi by 3 to naught of 3a squared 1 plus cos theta squared d theta. So that gives us a is equal to 9a squared over 2 pi by 3 to naught of, and let's square out that now, 1 plus 2 cos theta plus cos squared theta d theta. And how many times have we had to integrate cos squared or sine squared here with this type of question? I'm going to do it again, do it in a different colour. Cos 2a equals 2 cos squared theta minus 1. So cos squared theta minus 1, cos squared theta is equal to half cos 2a plus 1. Okay, let's go back to blue. So that means that this is equal to 9a squared over 2 pi by 3 naught 1 plus 2 cos theta plus a half cos 2 theta plus a half d theta. Okay, right, okay, so let's bring the two numbers together before I integrate. So that's 3 over 2 plus 2 cos theta plus a half cos 2 theta d theta. So now we can integrate. So it's 9a squared over 2 box 3 over 2 theta plus 2 sine theta plus a quarter sine 2 theta from pi by 3 to naught. Okay, so now we're in a position to put the limits in. First of all, the naught bit here is going to yield the answer naught. So I'm just going to work out the upper limit, input pi by 3 to this, because putting in 0, sine of 0 is naught, and obviously we're going to get naught here. So I can see that the naught's not going to matter. So it's 3 over 2 pi over 3 plus 2 sine pi over 3 plus a quarter sine pi over 3. And so the naught bit is not going to yield anything. So that will give us 9 over 2a squared. We're now going to get pi over 2 there. Plus, now this is 2 sine pi over 3. Now sine pi over 3 is the square root of 3 over 2, so that's square root of 3. But this one here is sine, I should have put 2 pi over 3. It's not actually change the answer, but it will be. It's not right, so we can't. 2 pi over 3. Sine 2 pi over 3 is also going to be square root of 3 over 2, so that's the square root of 3 over 8. So let's put over common denominator. That will, if I put all over 8, that will then, when it comes outside the bracket, there will be 16a squared. And we're going to have, in order to put that over 8 there, that will be 4 pi. And here we'll have 8 the square root of 3 plus another square root of 3, so that's 9 the square root of 3. And that's our answer. Oh, but wait a minute, if you look at the question, it'd be a bit annoying to miss out on it says P and Q are rational numbers. There is a danger of missing out on the final A mark here because of the thing they've asked it for. I actually think it's a bit annoying to lose the mark for that. So we do times the 9 over 16 inside. So that's A squared. 9 over 16 times 4, that would be 9 over 4 pi plus 81 over 16 the square root of 3. Okay. Right, okay, so let's look at the next question. That wasn't too bad for a polar coordinates question. Let's look at the next question. Taylor series, Maclaurin series. That's not normally the hardest questions, but let's see. There's always can be. Some of the differentiations can be tricky sometimes, so don't think this looks too bad. We're going to use the chain rule to differentiate. So we've got dy by dx is equal to 2 tan x to the power 1, if you like, sec squared x. Right, so now we're going to use a product rule on that. d2y by dx squared is, now differentiate tan x, you get sec squared, so that's 2 sec squared x times sec squared x. Now we need to differentiate the 2 tan x times sec x differentiated. Well, sec x differentiated is sec x tan x, but we've already got the sec x to the power 1, so that's going to be sec squared x there. So this is equal to 4 sec to the 4x plus 2 tan squared x sec squared x. But they want it in a slightly different form, so we need to replace our tan squared x plus 2. Now 1 plus tan squared x is sec squared x, so sec squared x, tan squared x is sec squared x minus 1. So that gives us what we need to get, I believe. Oh, there should be a 4 here, of course. One of these cases where it's an advantage, it's so that, because you don't get the answer that they expect. It's obviously a 4 because when we differentiated, we already had a 2. And then when we took the power of 2 down, we differentiated, we get a 4. So there we go. So then that makes, and we've still got a sec squared x there. So that gives us the what we want, 6 sec to the 4x minus, I've done something strange here. Seem to change a 2 to a 4 and a 4 to a 2. Anyway, there we go. That's 2 tan x there. So seem to have got those two the wrong way around. But anyway, we've got there. So it's 6 sec to the 4x plus because that's minus 4 sec squared x. We got there in the end. Wasn't particularly difficult either, but sometimes they get jumbled up like that. Okay, that's that one. Now let's do part B. d3y by dx cubed, well, we can easily differentiate each of these individually. I'd have thought d3y by dx cubed. That's going to be 24 because of the 4 times the 6 in this, sec cubed x, but don't forget to differentiate the inside, which is sec x, which is sec x tan x. That's the first term. And then the other one, 2 times 4, so that's minus 8. And that's going to be sec x to the 1, if you like. And then sec x differentiated again is sec x tan x. Okay, so it gives us d3y by dx cubed is equal to 24 sec to the 4x tan x minus 8 sec squared x tan x. And they said write it in this form, so we can take out the factor of 8. We're kind of reassured that we can write it in that form now. That's sec squared x tan x. That will make it 3 sec squared x minus 1. Okay, so now on to the Taylor series aspect of this. Up until the term x cubed, we need to find out y when x is pi by 3. Well, that's just tan pi by 3 squared, which is equal to 3, because that's the square root of 3 squared, which is 3. And then dy by dx, we've got an expression for that somewhere up here. Where have we put it? Dy by dx comes from here. Dy by dx at pi by 3 is equal to 2 tan pi by 3 sec squared pi by 3. That's cos squared. That's going to be tan pi by 3 is the square root of 3, so it's 2 times by the square root of 3. The sec squared is, well, it's just reciprocal of cos squared. Now cos squared pi by 3 is equal to a half, so that's equal to 4. So that's 8 the square root of 3. Okay, now d2y by dx squared at pi by 3 is equal to, we've got the thing that it has to, so it's 6 sec to the power 4 pi by 3 minus 4 sec squared pi by 3. Now sec to the 4 pi by 3, again sec pi by 3 is equal to 2, so that's 2 to the power 4, which is 16, so that's 6 times 16 minus 4 times 4. I'll be off cheat and use my calculator on that because mental arithmetic's failing me at the moment. That's equal to 80. Okay, and then d3y by dx cubed, x is pi by 3. Let's use the expression from here, so that's 8 sec squared pi by 3 tan pi by 3 over 3 sec squared pi by 3 minus 1. That equals to 8. Now we've already said that sec pi by 3 is equal to 2, so it's 8 times 4 times the square root of 3. 3 times 4 minus 1. So 3 times 4, which is 12 minus 1, is 11. So we've got 32 square root of 3 times by 11. Okay, so that's 11 times 32, 352. Square root of 3. Okay, so now we're ready to put into our Taylor series. So we've got, remember our Taylor series, let's write it out. Y is equal to, approximately equal to, obviously it's an infinite series. Y when at pi by 3 plus dy by dx at pi by 3 times by x plus d2y by dx squared at pi by 3 x squared over 2 factorial plus d3y by dx cubed at pi by 3 x cubed over 3 factorial. Okay, so that gives us y is approximately equal to our value for x, which we had y3, which is 3, plus 8 the square root of 3 times x, plus 80, but that's divided by 2, so that's 40 x squared, plus this number divided by 6. Now 352 divided by 6 is 176 over 3, so that's 176 over 3 x cubed. And that's our Taylor series question done. Not too bad, I'd say, relatively standard, although a bit tricky, just got to be careful, so there may be accuracy issues with some. Okay, right, now this nice question at the end. It came up on the overseas paper, I think, when they still had that overseas paper, so rather than the international one last year. It hasn't come up for a few years, so it's the kind of thing that if we hadn't seen this substitution ever before, and this is the first time you see it on this paper, it's when you do it in the exam, you've got to be kind of brilliant to be able to do it. It's the kind of thing that needs to be rehearsed and needs to be seen again and again, and you need to remind yourself kind of regularly how it works. Otherwise you may, well, an old-fashioned word, come a cropper. Okay, so x equals to e to the u is the substitution. We want to bring that down to something with y's and u's in it. So we can say dx by du is clearly equal to e to the u. So we can get an expression for dy by du, because dy by du is going to be equal, in terms of dy by dx that is going to be equal to dy by, let's do it in terms of dy by dx in fact. So let's just say dy by dx is equal to dy by du times by du by dx. Now du by dx is a reciprocal of this. Notice that this is equal to x. I'm going to e to the u is equal to x, so that means that this is equal to 1 over x. Let's write it the right way around, the same way around. dy by du, du by dx, which is the reciprocal of this, so that's 1 over x. So that, let's write that out again. dy by dx is equal to 1 over x dy by du. Okay, right, now then, so we're going to be able to replace our dy by dx in here with this expression here. Okay, so let's differentiate again. Okay, d2y by dx squared, we're going to use a product rule. Differentiating the 1 over x bit, no problem, minus 1 over x squared times by dy by du. Right, now differentiating the, we're going to times by the 1 over x times d by dx of dy by du. I love this one. This causes problems with some students because they just they fail to recognise the fact that we've got two different things we're differentiating with respect to here. So we can't just say that this is not equal to d2y by du squared, simply that, which is a common mistake that students make. Okay, it's actually equal to, let's just go back to, I will probably just write it out and then annotate later rather than do this. Minus 1 over x squared dy by du plus 1 over x. Now, if I differentiate it with respect to u, I can do that. But then I have to compensate for that, if you like, by times in by a dy by dx. I'll try and explain that, annotate that separately. Okay, what it is d by dx of dy by du is equal to, if we change a variable that we're differentiating it with respect to, by du, so that it is du by dx, but then we have to have a du by dx there to compensate, which actually shows you that I was wrong. Just as well I checked. It should be du by dx there. You can think of it almost, it's kind of nonsense maths really, but you can think of it almost as a du cancel in there. And then we've still got the dx that we're differentiating with respect to. Oh, just as well I checked that, otherwise it would have been wrong myself. So there we go. Just shows you we need strategies to kind of check our work sometimes. But the big wrongy is to miss this term out completely. Doesn't help to actually put a term in there and get it wrong, but we should at least recognise that we need another term. We can't just simply say it's d2y by du squared. Well, we've already got an expression for we've already got an expression here for du by dx, kind of, because we got du by dx here is 1 over x. You can see it from up here. Because it's a reciprocal of dx by du, which is 1 over x. So this is equal to minus 1 over x squared dy by du plus 1 over x squared d2y by du squared. Okay, so now we need to put this into a, put everything into this to check it works. So we've got x squared, this comes to x squared d2y by dx squared, which is this, that's minus 1 over x squared dy by du plus 1 over x squared d2y by du squared minus 7x times by 1 over x dy by du plus 16y is equal to 2 ln x. Now ln x, of course, will be equal to u, or 2, so that will be equal to 2u here. So multiplying out the x squareds, we can see we get minus dy by du plus d2y by du squared minus 7 dy by du plus 16y equals 2u, which gives us what we want, d2y by du squared minus 8 dy by du plus 16y is equal to 2u. Okay, so now we're going on to part B. So that was the tricky little confusing bit with the implicit differentiation. Okay, so let's go on to that. Okay, so we're on to part B, which is now we're really into standard stuff really. Let's look at the complementary, the auxiliary equation. We're going to work out the complementary function here first. So the auxiliary equation related to that is m squared minus 8m plus 16 equals 0. And that's m minus 4 equals to 0. So m minus 4 squared equals to 0. So that means that m equals to 4, so it's repeated. So the complementary function is y equals to a e to the 4x plus bx e to the 4x. Okay, because it's a repeated root on that one. Okay. So for a particular integral, because it's linear here, I'm going to try a linear function. So I'm going to try, for a particular integral, try y equals to a e. Oh, I've just realised I put x's in instead of u's here. Never mind. 4u and a u here. And a 4u here. So a is equal to, y is equal to au plus b. That gives me y dash is equal to a, and y double dash obviously equals to 0. So if I put those into my differential equation here, I get 0 minus 8 times dy by du, which is a, plus 16 times by the au plus b. It's got to be exactly the same as 2u. So we have 16 au plus 16b minus 8a has got to be equal to the same as 2u plus 0 if you like. So we've got 16, first of all we've got 2 must be equal to 16a, so that gives us a is 1/8. But also we've got 16b minus 8a must be equal to 0 because there's no constant term here. Okay, so there's no constant term there. So we've got a is 1/8, so that gives us b is equal to 1/16. So that's telling us the general solution is y equals to our auxiliary function, which is a e to the 4u plus b u e to the 4u plus, and we had 1/8 of, we have au, so that's 1/8 of u plus b, which was 1/16. But don't forget that we had this substitution right at the beginning, so we need to have it in terms of x. So we've got y, let's write it like this, a, that's e to the u to the power 4, plus b u e to the u to the power 4, plus 1 over 8 u, plus 1 over 16. So that gives us y equals to a x to the 4. Now u is obviously equal to ln x, so that's plus b ln x to the 4, plus 1 over 8 ln x, plus 1 over 16. And I think that was actually, I didn't realise I did it, but that's actually part C of the question, I believe. So that is done. So now we've done every question. Let's look at the, I just thought it might be good to reflect back on the whole paper that we've done over the 2 videos. First one, we preferred the squaring method, I think, although I did offer the alternative kind of critical value approach using a table, which I quite like with certain questions. The slight twist at the end that you had to recognise the modulus bit here actually meant that this solution here was not valid. So that's why we had that bit to the solution. I think I've actually written it out for part B. I might do that for part B. Yeah, it's so the answer to part B is x. It's got to be greater than 1. Okay, then slightly fiddly question on de Moivre's theorem. Found that using a diagram for the first part was better. Part B was using de Moivre's theorem with a positive power, not too difficult there, there's only one solution. But whenever you've got a fraction, whatever the denominator is, we've got quite a number of solutions. Seem to remember making a bit of a meal of that, never mind, got there. Question 3, standard integrating factor question. There were 2 possible integrations, I think, but it was pretty standard. Question 4, my favourite on the paper, because a little bit of a twist in it. It hasn't been couched in the normal terms. We had this theorem where we had to work it out, where we had to work through it, but we got there, so not too bad either. Well, I think talked to some students last year, did cause a few difficulties. Question 5, relatively nice transformations in the complex plane. It involved an area at the end. Whenever you have an area, modulus technique here, by the way, is the way to go here. And it probably comes up in many of the questions, probably quite a few of the questions, the modulus technique. When it can be employed, it's probably best to employ it. And then there was an area bit at the end. And we, in this video, we did a nice polar coordinate. Not really anything difficult about that one at all. Means a lie to the idea that polar coordinates has to be difficult. That's quite standard. Bit fiddly with our Taylor series. Have to be careful with chain rule. This is the kind of point, I suppose. If you're dodgy with your using the chain rule, I haven't used any U's or anything like that. We really need to be fluent with our use of chain rule here. So marking some people C3 recently, just not getting those kind of obvious applications of the chain rule and then the product rule to follow it. This one, I say, if it was the first time we saw that type of question, it would be probably pretty horrific. But in fact, looking at it here, it's not too bad at all, because we've seen it, that type of thing, many times. Okay, so that's it. Paper done. Hope you enjoyed it. Bye.